That dark patch in the Milky Way is not an empty void. It is a cosmic closet hiding profound secrets. These are dark nebulae, the universe's shadowy enigmas. They are dense clouds of gas and dust so thick they blot out the light of the stars behind them. But they are far more than just holes in the sky. They raise deep questions about how stars are born, how our galaxy is built, and what darkness truly means in the vastness of space. By the end of this journey, you will understand 25 of the most mysterious dark clouds that challenge everything we know. We will explore why a seemingly perfect cloud refuses to create a star and what happens when a stellar explosion slams into its own nursery. What cosmic mystery do you think is hidden within that darkness? A stark black patch hangs beside the Southern Cross, a void so deep it seems the stars have been torn away. This is the Coalsack Nebula, the most prominent dark nebula visible without a telescope. For centuries, cultures around the world have woven stories into its emptiness. Aboriginal Australian astronomers saw it as the head of a great emu in the sky, a celestial ancestor. Early European sailors viewed it as a foreboding omen, a literal hole in the heavens. Yet this is no mere absence of light. It is a dense, cold cloud of microscopic dust grains and molecular gas, a cosmic thunderhead so thick it completely obscures the stellar brilliance behind it. Its very presence raises fundamental questions. Pinpointing its exact mass is incredibly difficult, as we cannot simply count the stars it hides. Its composition is a complex cocktail of molecules, some of which are the very building blocks of life, all frozen within that dust. And its dramatic location, pressed right against the searing radiation of the bright stars in the Crux constellation, creates a turbulent frontier. How does that intense stellar wind sculpt the cloud, compressing some parts and eroding others? This proximity makes the Coalsack a perfect natural laboratory, a close-up view of the chaotic conditions that may eventually lead to the birth of new stars and planetary systems. Visuals of this region are breathtaking, showing an inky black silhouette set against the glowing river of the Milky Way. It is a reminder that the universe's greatest creations often begin in the deepest shadows. While the Coalsack is a sprawling shadow, another dark nebula presents a far more defined silhouette. In the sword of the mighty constellation Orion, the Horsehead Nebula stands as a cosmic icon. Its profile is unmistakable, a dark stallion's head seeming to emerge from a glowing pink sea of hydrogen gas. This is Barnard 33, a prototypical dark nebula that reveals the violent forces constantly reshaping our galaxy. It is not a static sculpture but a dynamic pillar of incredibly cold gas and dust, actively being sculpted and eroded by the intense ultraviolet radiation from Sigma Orionis, a brilliant young star located nearby. This stellar wind carves away at the cloud, giving the Horsehead its distinctive shape and boiling material off its surface in a visible haze. This raises a poignant cosmic question. Given the relentless assault from this stellar furnace, how long can this iconic structure possibly last? Astronomers estimate it may only persist for another 5 million years, a fleeting moment in cosmic time, reminding us that the universe's most beautiful formations are often temporary. Yet within that fleeting darkness, profound mysteries unfold. The dense core of the Horsehead is a shielded cosmic laboratory, so cold and rich with material that complex chemical reactions thrive. Within that icy dust, simple molecules collide and stick, forming complex organic compounds known as polycyclic aromatic hydrocarbons. These are the sprawling, carbon-based molecules that are considered fundamental building blocks of life. The nebula acts as a giant chemical factory, creating these precursors to biology in its deepest, darkest recesses. But observing this process or spotting the infant stars that are likely forming within this dense core is one of astronomy's greatest challenges. The very dust that creates the spectacular silhouette also blocks our view, hiding its secrets from optical telescopes. This is where instruments like the Hubble Space Telescope and especially the James Webb Space Telescope become our eyes. Hubble's visible light images show the stunning silhouette against the glowing gas, while Webb's infrared vision peers right through the dust, revealing the nebula's intricate internal structure and the faint glow of those nascent stellar objects. The Horsehead is not just a pretty face in the cosmos, it is a window into the chaotic and creative processes that occur within every dark cloud. Slithering through the star fields of Ophiuchi, the Snake Nebula is a shadowy filament that defies simple explanation. IT's Chinese letter serpentine body is not a solid object but a delicate thread of cosmic soot and cold gas, a perfect example of the intricate filamentary structures that lace the entire interstellar medium. This leads us to a profound physical mystery. What cosmic forces are capable of sculpting such a long, impossibly thin shape across the void? The answer likely lies in a complex interplay of powerful but invisible influences. Intense magnetic fields woven through the galaxy could be channeling and confining the cloud's material, squeezing it into this narrow, winding river of dust. Alternatively, supersonic turbulence from ancient supernova explosions might be whipping the gas into these elongated, rope-like tendrils. To solve this, astronomers turn their radio telescopes toward the serpent. These instruments can peer into the dark cloud, mapping the subtle motions of its internal gas. By tracing its velocity structure, they can listen to the nebula's hidden dynamics. Is the cloud a stable, quiescent structure simply drifting through space? Or are there subtle, inward motions, the telltale signs of gravity beginning to overpower internal pressure, pulling the snake into dense knots that will one day ignite as new stars? The Snake Nebula is more than a celestial curiosity. It is a crucial piece in the puzzle of how diffuse cosmic material gathers itself together, taking the first silent steps toward creating everything we see in the night sky. Far from the intricate filaments of the snake, another dark nebula paints a broader, more recognizable picture against the Milky Way. This is the Pipe Nebula, a sprawling complex of dark clouds that forms the unmistakable silhouette of a smoker's pipe, complete with a bowl and a long stem. Its components, known to astronomers as Barnard 59, 65-67, and 78, are not a single object but a family of dark nebulae that together create one of the largest and most distinct shapes in the night sky. This entire structure is itself just the head and neck of an even vaster formation known as the Dark Horse Nebula, a colossal shadowy figure that seems to gallop across the star clouds near the center of our galaxy. The sheer scale of the pipe is humbling, stretching across a significant portion of the sky, but this two-dimensional view raises a deeper, three-dimensional puzzle. When we look at this cosmic pipe, are we seeing a flat drawing on the celestial sphere, or a truly interconnected structure stretching through space? Determining how its stem physically connects to its bowl, or how deep this cloud extends into the galactic backdrop, is a challenge of cosmic cartography. The answer lies in painstaking measurements of distance, using data from observatories like Gaia to map the precise locations of the few stars visible in front of and behind the dust. This reveals the pipe not as a simple painting, but as a sculpted landscape of peaks and valleys of obscuring dust, some parts much closer to us than others, creating an illusion of unity from our earthly perspective. Yet within its darkest recesses, something is stirring. Optical telescopes see only an impenetrable blackness, but the infrared eyes of telescopes like Spitzer and Herschel can peer straight through the dust, revealing the faint, warm glow of nascent stars buried deep within the cloud's core. These are young stellar objects swaddled in thick cocoons of gas and dust, slowly accumulating mass and beginning their long journey toward ignition. Their presence confirms that the Pipe Nebula is not a sterile void but an active stellar nursery. The question then becomes, what triggered this star formation? Was it a natural collapse under the cloud's own gravity, or was it spurred by an external shock wave, perhaps from a nearby supernova whose blast wave compressed the gas just enough to tip the scales? The pipe's quiet darkness is an illusion, masking the vibrant and violent birth of new suns. But within the sprawling Pipe Nebula, the story of star birth is still one of inference glimpsed from the outside. To witness the process in action, we must travel to our own cosmic backyard. Just over 400 light-years away, a chaotic and beautiful tapestry of creation is unfurling. The Rho Ophiuchi Cloud complex is a vibrant stellar nursery, so close that its dark lanes are not just silhouettes but intricate structures we can study in astonishing detail. While often photographed for its stunning blue reflection nebulae and glowing red hydrogen, the true heart of this complex lies in its vast inky black dust clouds. These are not empty voids but a rich molecular soup, a frigid reservoir of gas and dust so dense it blots out the starlight from behind. This proximity makes Rho Ophiuchi a perfect laboratory, raising critical questions about the very efficiency of star formation. Why do some dense pockets within these dark clouds collapse furiously into brilliant new suns, while other, seemingly identical clumps of gas remain stubbornly dormant? The answer appears to be written in the violence of its own children. Scattered throughout the complex are massive young stars like the brilliant red supergiant Antares. These stellar behemoths are cosmic tyrants, unleashing ferocious winds of charged particles that scream outward at millions of miles per hour. When these hurricane-force winds slam into the surrounding dark clouds, they do two contradictory things. In some regions, the wind acts like a cosmic sculptor, compressing the gas and dust with immense pressure. This shockwave can push a stable cloud over the edge, triggering a sudden and dramatic collapse that ignites a new generation of stars. Yet, in other areas, that very same stellar wind is a force of pure destruction, stripping material away from the cloud, tearing apart potential stellar cradles before they can even form. This creates a chaotic and unpredictable landscape of creation and demolition happening side by side. One of the great mysteries of Rho Ophiuchi is determining the ultimate fate of these dark clouds. Will they be the birthplaces of future solar systems, or will they be completely evaporated, their potential unspent, scattered back into the diffuse interstellar medium? It is a dramatic reminder that the birth of stars is not a gentle process, but a turbulent battle between the crushing force of gravity and the explosive power of stellar radiation. In the heart of Ophiuchus hangs a darkness so absolute it seems like a perfect circle punched from the starry canvas. This is Barnard 68, a celestial phantom that defies the chaotic shapes of other nebulae. Its form is a near-flawless sphere, an ink blot of cold gas and dust so dense that not a single visible star from our galaxy can be seen through its core. Astronomers classify it as a Bok globule, a specific type of small, isolated dark nebula, and Barnard 68 is perhaps the most perfect example ever found. Its symmetry is so striking that it has become a cosmic standard, a laboratory in the sky for studying a process known as interstellar extinction. This is simply the measure of how much starlight is absorbed and scattered by dust grains as it travels through a cloud. Because Barnard 68 is so isolated and symmetrical, scientists can precisely calculate how its dust dims and reddens the light from the background stars at its edges, giving us a fundamental ruler for understanding the properties of cosmic dust everywhere. Yet this beautiful simplicity masks a deep and puzzling mystery. Here we have a cloud of gas, cold and dense, seemingly ripe for star formation. Gravity should be pulling this material inward, causing it to collapse under its own weight until the core ignites into a new sun. So why does Barnard 68 remain stubbornly dark and silent? What invisible force is holding back the inevitable crush of gravity? the leading hypothesis points to the cloud's own internal thermal pressure. The molecules inside, though frigid, are still in motion, and this gentle, persistent heat generates an outward pressure that can support the cloud against its own weight, like a faint, warm breath inflating a cosmic balloon. Another possibility involves weak magnetic fields threading through the globule. These fields can act like a flexible cage, providing additional support to keep the gas from collapsing. But are these forces enough to maintain this perfect equilibrium indefinitely, or are we simply catching this globule in a fleeting moment of stability? To solve this, astronomers have turned our most powerful infrared eyes toward its heart. Telescopes like the Very Large Telescope and the James Webb Space Telescope can peer through the dust, searching for the faintest warmth that would betray a hidden protostar, a baby sun still gathering its mass in the deepest dark. So far, the search has found nothing. Barnard 68 appears to be truly dormant, a cosmic egg waiting for a signal to hatch. The question of what that signal might be, what final push will break this delicate balance and begin the process of creation, remains one of the most intriguing puzzles in the study of these dark nurseries. Rising from a turbulent sea of glowing gas, the Cone Nebula presents a far more violent and dramatic scene than the silent sphere of Barnard 68. Located in the constellation Monoceros, this colossal dark pillar is a staggering 7 light-years long, a monument to the destructive power of starlight itself. Its sharp, conical shape is not a product of random chance, but is meticulously carved by the fury of a nearby cluster of massive, brilliant young stars. These stellar giants flood the region with intense ultraviolet radiation and powerful stellar winds, a hurricane of energy that acts like a cosmic sandblaster. It systematically evaporates the less dense material of the surrounding cloud, while the densest, coldest gas at the core resists the onslaught, left standing as a towering pillar. This process of photoevaporation raises an immediate question about the pillar's own fate. How long can this structure withstand such a relentless assault? The very forces that sculpted it are now slowly eroding it, boiling material off its surface in a visible haze that streams away from the tip. Within this chaotic environment lies a profound puzzle about the nature of creation. Astronomers have long suspected that the very tips of these dark pillars, compressed by the immense external pressure from the stellar winds, could be the ultimate stellar incubators. The intense pressure might trigger the collapse of the dense gas, leading to a focused burst of star formation right at the point of greatest danger. But is this actually happening? Observations from the Hubble Space Telescope have peered deep into the cone's dark tip, searching for the infrared glow of young stellar objects hidden within. The results are complex, suggesting that while some protostars may be present, the process is not as straightforward as a simple collapse. This leads to a deeper question, one that touches the very origin of stars like our own Sun. If stars are born in such pressured environments, what ultimately determines their final mass? Why does one pocket of gas become a red dwarf star, barely massive enough to shine, while another transforms into a brilliant blue giant? The answer may lie in the delicate balance between the crushing force of gravity pulling material inward and the opposing pressure from the growing protostar's own heat and magnetic fields, a battle whose outcome is written in the turbulent currents deep inside the dark pillar. The Cone Nebula stands as a stark reminder that in the cosmos, the cradles of new life are often found in the shadow of destruction. Stretching like a celestial serpent across the southern constellation Musca, the dark Doodad Nebula presents a different kind of challenge. Its name, playful and informal, belies its scientific significance. This is not a bold, iconic silhouette like the Horsehead, but a long, slender river of darkness, a filament so subtle it tests the very limits of visibility and photographic skill. For amateur astrophotographers, capturing the Doodad's full, delicate length is a coveted achievement, a testament to both dark skies and technical patience. Its faint, ethereal form immediately raises a fundamental question of cosmic geometry. When we trace this seemingly continuous dark lane, are we looking at a single, coherent cloud, a physically connected structure drifting through space? Or is its unity an illusion, a simple chance alignment of multiple, unrelated dust clouds that just happen to fall along our same line of sight, creating the appearance of a single object from our earthly vantage point? This is not merely an academic debate. The answer dictates everything we can learn from it. If the doodad is one object, then its incredible length implies a truly massive and stable structure, raising questions about what forces could bind such a slender cloud together against the galaxy's turbulent tides. But if it is multiple clouds at different distances, then its apparent form tells us little about its true nature. Resolving this mystery hinges on a single, critical measurement: distance. By using precision data from observatories like Gaia to pin down the exact locations of the stars peppering its edges, astronomers can build a three-dimensional map. They can determine whether the dust obscuring those stars lies at a consistent distance from us, confirming a single cloud, or is scattered at various depths, revealing a phantom. Only with an accurate distance can we then calculate its true physical size, and from that, its total mass. Without this knowledge, the dark doodad remains a beautiful enigma, a shadow on the sky whose true scale and significance are still hidden in the dark. While the dark doodad's slender form is a test of observation, the vast majority of dark nebulae are not iconic silhouettes at all. They are the background characters of our galaxy, countless shadows catalogued by their simple coordinates. One such object is LDN 1774, a typical dark cloud drifting through Ophiuchi. It lacks a memorable shape or a dramatic story, yet its very anonymity makes it profoundly important. LDN stands for the Linz Dark Nebulae Catalogue, a monumental survey that mapped over 1,800 individual clouds of obscuring dust. LDN 1774 is just one entry in this vast cosmic census, a single face in a crowd of thousands. This sheer ubiquity forces a fundamental shift in perspective. Dark nebulae are not rare cosmic curiosities. They are a fundamental component of the Milky Way's architecture. They are the raw, unprocessed material from which the galaxy continually rebuilds itself. Visuals comparing the dramatic Cone Nebula or the iconic Horsehead to the faint, formless smudge of LDN 1774 would reveal a stunning diversity from towering pillars to ragged patches. But this typical cloud raises a deeply statistical question about star formation itself. If the galaxy is filled with so many similar clouds of cold gas, each one a potential stellar nursery, why do so few of them actually ignite? What are the precise initial conditions that tip a stable, quiescent cloud like LDN 1774 into a dramatic gravitational collapse? Is it a specific density threshold, a critical level of internal turbulence, or does it always require an external trigger, like the shock wave from a distant supernova? This unremarkable nebula represents the silent majority of cosmic gas clouds, the vast reservoir of potential that has not yet been activated. Studying it and its countless cousins is not about finding a single answer, but about understanding the odds. It prompts us to ask what fraction of this dark material will ever become stars, and what fraction will simply drift for eons, never fulfilling that latent promise. The mystery of LDN 1774 is the mystery of unrealized potential on a galactic scale. An ink blot of absolute blackness floats in a sea of stars, a tiny void so dark it appears two-dimensional. This is Barnard 86, the Ink Spot Nebula, a compact dark cloud that creates one of the most startling contrasts in the entire night sky. It sits right beside the brilliant open star cluster NGC 6520, a sparkling jewel box of hot, young blue stars. The visual pairing is breathtaking, a perfect cosmic diorama of light and shadow. The ink spot's profound darkness is a textbook example of interstellar absorption, where an exceptionally dense concentration of dust grains completely extinguishes the light of every star behind it. This stark juxtaposition immediately presents a fundamental question of cosmic relationship. Are these two neighbors, the dark cloud and the bright cluster, intimately connected, or is their proximity merely a chance alignment, a beautiful celestial illusion? The answer lies in their shared history. One compelling theory suggests that Barnard 86 is the leftover debris from the very same giant molecular cloud that collapsed to form the stars of NGC 6520. In this scenario, the bright cluster represents the successful offspring, while the ink spot is the unused placental material, a cold remnant cast aside after the star-forming frenzy concluded. The alternative is that they are complete strangers, with the dark nebula being a much smaller, unrelated cloud drifting through the galactic disk that just happens to fall directly in our line of sight to the more distant cluster. To solve this, astronomers turn to the science of motion, performing intricate kinematic studies. By using the Doppler shift in radio waves, they can measure the precise velocity of the gas within Barnard 86 as it moves toward or away from us. Simultaneously, data from satellites like Gaia provide the exact motion of the stars in NGC 6520 through space. The critical test is to see if their paths are synchronized. If the nebula and the cluster share the same direction and speed, it is powerful evidence they were born from the same cloud and are still traveling together as a family. If their motions diverge, it proves they are unrelated strangers, their beautiful pairing only temporary from our unique vantage point. This tiny ink spot is more than a dark smudge. It is a cosmic crime scene where astronomers gather forensic evidence to trace the origins of stars and the dusty clouds they leave behind. Curling through the glowing heart of the immense IC 1396, a dark, sinuous form reaches out into the void. This is the Elephant's Trunk Nebula, a colossal pillar of cold gas and dust that seems to defy the blistering radiation surrounding it. But its survival is an illusion, a dynamic and violent balancing act. At the center of this vast emission, Nebula burns a brilliant, massive star, a stellar titan pouring forth intense ultraviolet light. This radiation acts like a cosmic blowtorch, relentlessly heating and evaporating the surface of the dark globule, boiling material away into space and giving the trunk its sculpted teardrop shape. This process, known as a radiation-driven implosion front, presents a profound cosmic contradiction. How can this destructive force of erosion also be the very trigger for new creation? The answer lies in the immense pressure. The stellar radiation does not just strip material away, it also compresses the cloud with overwhelming force. The blast of energy pushes inward, creating a shock wave that travels through the globule, squeezing the gas and dust to ever higher densities. In this cosmic pressure cooker, pockets of gas that were once stable can be pushed over a critical threshold. Their own gravity, now amplified by the external pressure, suddenly wins the battle and they begin to collapse. This is not a gentle nurturing but a violent, forced birth. The evidence for this is buried within the trunk's darkest folds. Infrared telescopes have pierced the obscuring dust, revealing the telltale warmth of young stellar objects, protostars deeply embedded within the pillar itself. Even more dramatic are the Herbig-Haro objects discovered there. These are not the stars themselves, but brilliant, narrow jets of superheated gas, fired out at supersonic speeds from the poles of these infant suns as they actively accrete material from their surrounding disks. We are witnessing stellar birth in real time, a process directly ignited by the very star that is simultaneously destroying the nursery. This creates a poignant race against time. Will these new stars gather enough mass to become stable before their protective cocoon of gas is completely evaporated by their brilliant, destructive neighbor? The elephant's trunk is a stunning demonstration that in the cosmos, creation and destruction are two sides of the same violent, beautiful coin. Soaring through the constellation Cepheus, the dark nebula Barnard 163 presents a shape both whimsical and deeply puzzling. Its silhouette strongly resembles a celestial duck, complete with a rounded head and an elongated body, floating serenely against the glowing backdrop of the Milky Way. But this is no tranquil pond. Barnard 163 is embedded within the immense and turbulent IC 1396 emission nebula, a cauldron of star formation also home to the elephant's trunk. This duck's cometary appearance, with a bright, curved rim and a long, trailing tail of darkness, is the first clue that it is not an isolated, stable cloud. That streamlined shape is the classic signature of a cloud being hammered by an external force. The question is, what is sculpting this dark avian form, and what is its ultimate fate? The likely architects are the powerful OB associations in the region, sprawling groups of massive, hot, and short-lived stars. These stellar giants flood their surroundings with intense radiation and supersonic stellar winds, creating a pervasive, high-pressure environment. Barnard 163 is caught in this cosmic gale. The bright rim we see is the side of the cloud facing the stellar fury, where the incoming radiation is compressing and heating the dust, creating a sharp boundary. The duck's long, dark tail is the sheltered wake of denser material trailing behind, protected from the direct blast. This dynamic raises a critical question about the cloud's evolution. Is it a stable structure that can withstand this pressure for eons, or is it in the process of being actively dispersed, its material slowly evaporating back into space? The evidence points toward a dramatic and transformative process. This very pressure may not just be destroying the cloud, but also triggering new life within it. This leads to the profound concept of sequential star formation. Imagine a chain reaction on a cosmic scale. The first generation of massive stars in the OB association lives fast and dies young, exploding as supernova. The shockwaves from these colossal detonations race outward through space, slamming into nearby dark clouds like Barnard 163. This immense wave of pressure sweeps through the cloud, crushing the gas and dust and pushing stable pockets over a critical density threshold. Gravity then takes over, causing these compressed knots to collapse and ignite, birthing a second, new generation of stars. This cycle of death leading to life could be precisely what is happening within the duck's dark body. The intense external pressure from the OB association might be providing the final push needed to initiate the collapse of pre-stellar cores hidden within its form. So, when we look at the whimsical shape of Barnard 163, we are likely witnessing a single snapshot in a grand, self-perpetuating cycle. It is both a remnant of an earlier era of star birth and a potential cradle for the next, its evolution dictated by the violent winds of its brilliant neighbors. This vast division in the Milky Way is not a true void, but a mountain range of shadow. The Great Rift in Cygnus is a colossal complex of dark nebulae, an interstellar dust lane so immense it appears to split our galaxy's bright band in two. This is not one single object, but a sprawling network of hundreds of individual clouds, a contiguous structure stretching hundreds of light years across space. Its sheer scale presents one of the most fundamental challenges in mapping our own galaxy. What is the total mass of this entire complex, and how is its material truly distributed in 3 dimensions? From our vantage point inside the galactic disk, we see this dust as a 2-dimensional dark river, but it has depth and texture, with some clouds much closer to us and others lying far toward the galactic center. This obscuration has a profound consequence. It completely blocks our optical view of the heart of the Milky Way. The brilliant, dense cluster of stars surrounding the supermassive black hole at our galaxy's core is hidden from our sight, veiled behind this seemingly impenetrable dark curtain. But where optical light fails, other wavelengths reveal a hidden universe. This same dust that blocks visible light glows with its own faint warmth in the infrared. Space telescopes like Spitzer and Herschel have mapped the rift's intricate structure in stunning detail, seeing not a void but a vibrant landscape of cold, dusty filaments. Meanwhile, radio telescopes can peer straight through the dust, detecting the faint emissions from molecules like carbon monoxide within the clouds themselves. This allows astronomers to perform a kind of cosmic cartography, building a three-dimensional model of the rift's structure by measuring the velocities of these clouds as they orbit the galactic center. The Great Rift, therefore, is far more than a beautiful absence of light. It is both a major obstacle and a fertile ground for discovery, a reminder that our view of the cosmos is always filtered, and that the greatest mysteries often lie in what we cannot directly see. Deep within the constellation Lupus, the dark cloud Lupus 3 offers a rare and precious glimpse into the childhood of stars. Unlike the dramatic pillars being eroded by brilliant neighbors, Lupus 3 is a quieter, more isolated nursery. Its darkness is punctuated by tiny, piercing points of light, infant stars that have recently emerged from their dusty cocoons. These are T Tauri stars, the stellar equivalent of newborns, still contracting under their own gravity and prone to fiery tantrums of intense X-ray and ultraviolet radiation. This scene is a snapshot of early stellar evolution, a moment frozen in cosmic time just a few million years after the main collapse began. But what event set this entire process in motion? The presence of this active cluster raises a pivotal question about its origin. Was the trigger internal, a simple case of the cloud's own gravity finally winning a long, silent battle against internal pressure? Or was it an external cataclysm that shocked the cloud into collapse? One compelling suspect is a supernova shockwave. A massive star dying in a violent explosion somewhere nearby could have sent a powerful pressure wave racing through the interstellar medium, slamming into the stable Lupus 3 cloud and compressing it just enough to ignite star formation. Another possibility is a cloud-cloud collision, where two smaller, unrelated dark nebulae drifted into one another, their chaotic merger creating dense, turbulent knots that then collapsed under their own weight. To solve this cosmic cold case, astronomers turn detective, using the stars themselves as witnesses. By meticulously measuring the precise ages of the T Tauri stars in the cluster, they can look for a telling pattern. If all the stars are virtually the same age, it points to a single, sudden triggering event, like a supernova blast, that set off a synchronized burst of star birth. If, however, the stars show a spread of ages, with some being slightly older than others, it suggests a more gradual, internally driven collapse that propagated through the cloud over time. Furthermore, by using observatories like Gaia to track the subtle motions of these young stars through space, scientists can see if they are all moving together as a cohesive group, which would support a common origin from a single collapsing cloud. Or if their paths are diverging, it might hint at a more chaotic birth from multiple colliding gas clouds. Lupus 3 is more than a collection of young stars, it is a celestial clock, and by reading its hands we can trace the violent or serene events that led to its creation. While Lupus 3 reveals the fiery youth of stars, a much closer and quieter nursery holds the secret to our own origins. Drifting just beyond the Pleiades, the Taurus molecular cloud is a sprawling complex of dark nebulae, one of the nearest and most extensively studied star-forming regions to Earth. Its dark, meandering lanes and countless Bok globules are not lit by massive, brilliant stars, but instead serve as the secluded cradles for solitary suns. This calm, fragmented cloud presents a profound cosmic puzzle. Why does Taurus almost exclusively give birth to gentle, low-mass stars like our own Sun, often in complete isolation, while regions like Orion create dense, glittering clusters dominated by stellar giants? The answer appears to be written in the cloud's fundamental personality. Unlike the dense, tumultuous cores of other nurseries, the Taurus cloud is remarkably quiescent and has a relatively low overall density. Its gas and dust are spread out in a more placid, filamentary structure. This lack of intense crowding means that when a pocket of gas does collapse, it typically forms a single, small star rather than triggering a chain reaction that leads to a packed stellar family. This serene environment is further shaped by two invisible forces. The cloud possesses a significant level of internal turbulence, a kind of churning motion that can prevent large volumes of gas from coalescing into a single, massive core. More importantly, the Taurus cloud is threaded with a strong and ordered magnetic field. This magnetic architecture acts like a cosmic skeleton, providing support against gravity's pull. It can effectively compartmentalize the cloud, preventing the large-scale flows of material needed to build truly massive stars, and instead fostering the slow, steady growth of many individual, low-mass stars in relative solitude. So when we look at the dark, unassuming nebulae of Taurus, we are likely seeing a portrait of our own sun's humble beginnings. A single star born from a quiet, magnetized cloud, untouched by the violent dramas of a dense cluster. It raises a compelling possibility. Could the gentle conditions that forged our solar system be the cosmic norm, with the brilliant, clustered factories being the dramatic exception? Hidden within the faint constellation of Cygnus, a seemingly insignificant smudge of darkness holds a secret caught in a fleeting moment of transformation. This is LDN 1014, a dark nebula that has become a cosmic time capsule, preserving one of the most elusive stages in all of star formation. Within its cold heart, astronomers discovered not a fully formed protostar, but something even rarer and more primordial, a first hydrostatic core. This object represents a star's very first breath, the precise instant when a collapsing cloud of gas stops behaving like a shapeless fog and takes its initial step toward becoming a true sun. The process begins when a dense knot within the dark nebula, compressed by its own gravity, grows so hot and dense at its center that the internal pressure can finally support its own weight. This creates a stable, albeit tiny, core about the size of Jupiter's orbit, glowing faintly with the heat of collapse. But this balance is incredibly fragile, lasting a mere few thousand years before rising temperatures trigger the breakdown of hydrogen molecules, a change that causes the core to collapse once more, igniting the nuclear furnace of a true protostar. The profound question LDN 1014 forces us to ask is what specific set of initial conditions are required to cross this threshold. What precise density, what exact temperature, what minute level of rotation or magnetic field strength marks the point of no return for a cloud like this? Observing a first hydrostatic core is like catching a single frame from a movie that has been playing for millions of years, a snapshot of the decision itself. It allows scientists to test their complex simulations of gravitational collapse against a real, observed object. They can measure its luminosity, its size, and the outflow of material from its poles, comparing this data to theoretical predictions. Every measurement refines our understanding of that critical tipping point, the moment a random pocket of cosmic dust commits to a destiny of light and heat that could last for billions of years. LDN 1014 is more than a dark cloud. It is a window into the universal recipe for a star, revealing the delicate and brief infancy that precedes the brilliant dawn of any sun. Towering over the star fields of Scorpius, the Dark Tower Nebula stands as a colossal chess piece of cosmic dust. This immense pillar, part of the vast NGC 6231 complex, shares a silhouette with the famous pillars of creation but cloaks itself in far deeper shadow. Its dramatic shape is a direct product of its brilliant but destructive neighbors. The nearby star cluster NGC 6031 is a cauldron of massive, hot stars, and their relentless output of ultraviolet radiation acts like a celestial sandblaster. This energetic wind has spent eons scouring away the less dense material of the original cloud, leaving only the most resilient, dense core standing as this monumental tower. The very morphology of the pillar, its sharp edges and intricate contours, is a frozen record of this erosion. By reading its shape, astronomers can decipher the history and intensity of the radiation field that sculpted it. A sharper, more defined pillar suggests a more direct and potent blast, while a more ragged structure might indicate a more turbulent or varied erosive history. To see this violent interaction in action, we must look beyond visible light. In a multi-wavelength view, a fascinating detail emerges. The very tip of the dark tower, the part facing the full fury of the stellar cluster, often glows with a faint pinkish hue. This is the unmistakable signature of shocked hydrogen gas. As the stellar winds slam into the dense pillar at supersonic speeds, they compress and heat the gas at the interface, causing it to fluoresce. This glowing rim is the direct evidence of the ongoing battle, the contact point where the destructive power of starlight meets the stubborn resistance of cold dust. It raises a compelling question about the pillar's interior. Is this external pressure simultaneously triggering a final, frantic burst of star formation within the tower's shielded heart? Or are we witnessing the last stand of a structure destined for complete dissolution? The Dark Tower is not a static monument, but a dynamic landscape, its form narrating an epic story of radiation and resistance written across the light years. Barnard 342 is a perfect picture of cosmic stillness, a dark nebula that simply refuses to create. While other clouds are vibrant stellar factories, this one remains a silent, quiescent reservoir of cold gas and dust. Its profound inactivity forces a fundamental question upon us. What are the precise on and off switches for star formation? What pushes a stable cloud over the edge into the brilliant chaos of collapse? The answer lies in a delicate cosmic balancing act, a battle between three critical forces. First, the cloud must achieve a sufficient density, packing enough mass into a small enough volume for its own gravity to become overwhelming. Second, its internal temperature must drop low enough as colder gas exerts less outward pressure to resist the inward crush. And third, the cloud must settle its internal turbulence, the churning motions that can effectively prop it up and prevent a cohesive collapse. Barnard 342 appears to be lingering just below all of these thresholds. It may still be in the process of slowly gathering mass from the surrounding interstellar medium, a patient accumulation that has not yet reached a critical point. Alternatively, its stability could be artificial, maintained by the gentle but persistent warmth of its own gas or by a network of internal magnetic fields that act like a rigid scaffold, holding the cloud up against its own weight. This dark nebula is a crucial control subject in the grand experiment of star birth. By studying its quiet state, we gain a clearer understanding of what is missing, of the exact trigger that has not yet been pulled. It represents the vast majority of cosmic material, the silent potential waiting in the wings of the galaxy for a signal to begin. A dark gulf carves a familiar shape into the starry sky. Known informally as the Gulf of Mexico Nebula, this region is a masterclass in celestial interplay where darkness and light are locked in a delicate dance. It is not a single entity, but a complex of different nebulae, a partnership between the dark cloud Lyn's bright Nebula 140 and the glowing gases that surround it. This cosmic geography immediately raises a compelling question about the relationship between these shadowy forms and their luminous neighbors. How does a dark nebula, an apparent void, actively shape the brilliant structures we see? The answer reveals that these dark clouds are not passive silhouettes but dynamic participants. One of their most crucial roles is that of a cosmic shield. When a brilliant, massive star floods its surroundings with intense ultraviolet radiation, that energy ionizes the surrounding hydrogen gas, causing it to glow as a vibrant red emission nebula. But a dense, intervening dark nebula like the one in the Gulf of Mexico can cast a profound shadow. It acts as a protective barrier, blocking that harsh stellar radiation and leaving a sheltered, dark bay behind it. In this shadow, the gas remains neutral and dark, creating the stark, familiar outline of the Gulf against the bright background. Without this dark shield, the entire region might simply be a uniform, glowing sea of ionized gas, its distinctive shape lost. Yet, these dark clouds are also reservoirs of potential brilliance. The same cold, dense material that today appears as a black void is the raw fuel for future stars. When new stars ignite within or near these dark clouds, their light does not always ionize the gas. Instead, it can simply reflect off the dust particles, creating the soft blue glow of a reflection nebula. This is the other side of the partnership. The dark nebula provides the physical material, the dusty canvas upon which the starlight paints its masterpiece. The Gulf of Mexico Nebula showcases this beautifully, with its dark bays set against both the glowing red of emission and the subtle blue of reflection. So, when you look at this celestial map, you are seeing a snapshot of a continuous cycle. The dark nebula is both a protector, defining the shape of the light, and a womb, holding the very material that will one day be sculpted and illuminated by the next generation of stars. It forces us to reconsider the very nature of darkness in space, not as an emptiness, but as a creative and defining force. Its stark silhouette in the southern constellation Musca offers a different kind of clarity. The Musca dark cloud is not a dramatic pillar or a whimsical shape, but a relatively simple, isolated dark nebula. This very lack of complexity makes it a perfect cosmic laboratory, a controlled environment to ask fundamental questions about the chemical richness hidden within such shadows. The profound question it raises is not about its shape but its substance. In the deep freeze of its interior, where temperatures hover just a dozen degrees above absolute zero and the darkness is absolute, what complex molecules are being silently forged? The answer, revealed by the sensitive ears of radio telescopes, is astonishing. These instruments tune into the faint whispers of molecules tumbling in space, and they have mapped a veritable chemical factory within Musca. They have detected the simple, abundant signature of carbon monoxide, a fundamental tracer of cold molecular gas, but they have also found a growing inventory of more complex organic molecules, things like cyanopolyeins, long carbon chains studded with nitrogen atoms. These are not the building blocks of life itself, but they are the initial chemical steps, the complex precursors that form in the icy mantles of dust grains through a slow, cold chemistry. This process is thought to be the universe's first draft of organic chemistry, the initial scribbles that could one day, in the warmer environment of a developing planetary system, lead to the amino acids and nucleobases that form life's foundation. The Musca cloud's isolation is key, as it allows astronomers to study this chemical enrichment without the complicating glare of nearby massive stars. Its darkness is not sterile but seething with a quiet, molecular creativity, suggesting that the potential for life's ingredients may be a common and very dark beginning. Deep in the chaotic heart of our galaxy, a cosmic anomaly defies all expectations. This is the Brick, a dark nebula officially known as G 0.253 plus 0.016. It is one of the most massive and dense clouds of gas ever discovered, a colossal chunk of cold dust and molecules weighing over 100,000 times more than our own Sun. With so much raw material packed into a relatively small volume, you would expect this place to be a frenzied stellar factory, blazing with the light of countless newborn stars. Yet it is profoundly, mysteriously silent. The Brick raises the ultimate question about star formation. Why, with every ingredient for a brilliant firestorm seemingly present, does this cloud refuse to light up? The answer appears to lie in the uniquely hostile environment of the galactic center, a region of extreme physics unlike anywhere else in the Milky Way. Here, the supermassive black hole Sagittarius A star dominates, creating ferocious tidal forces that constantly stretch and pull at the cloud, preventing its gas from settling into a stable collapse. Furthermore, the entire region is laced with powerful, ordered magnetic fields. These fields act like a cosmic skeleton, providing a rigid support structure that holds the cloud up against its own immense weight. Add to this a cauldron of intense turbulence, with supersonic waves of energy crashing through the interstellar medium, and you have a perfect storm of suppression. The internal turmoil keeps the gas churned up and agitated, making it impossible for gravity to get a cohesive grip. This makes the brick a crucial laboratory for understanding star formation under duress. It demonstrates that having the mass is not enough. The cloud must also find a moment of quiet, a lull in the galactic storm, for gravity to finally whisper its command and begin the work of creation. Floating like dark tadpoles in a brilliant cosmic pond, Thackeray's globules present a scene of beautiful fragility. These are not the immense pillars of the Cone Nebula, but small, isolated Bok globules adrift within the searing glow of the Lambda Centauri Nebula. Each one is a compact capsule of cold gas and dust, a potential stellar cradle that has found itself in the most perilous of neighborhoods. The Lambda Centauri Nebula is a cauldron of intense ultraviolet radiation powered by massive, brilliant stars. This energy floods the entire region, and the globules are completely immersed in it. This creates a staggering visual contrast with the Inkai black spheres set against a backdrop of luminous pink gas. The iconic Hubble image of these globules is not a portrait of serene coexistence, but a snapshot of a violent confrontation. You can actually see the stellar radiation boiling material off the surfaces of the clouds, creating shimmering, evaporating streams of gas that trail away from them like cosmic smoke. This forces a critical question. With their material being stripped away so visibly, how can these delicate structures possibly survive long enough for stars to form inside them? The answer lies in a desperate race against time. The same radiation that is destroying the globules is also compressing them. As the outer layers are blasted away, the intense external pressure squeezes the inner core of the cloud, potentially increasing its density to the point where gravity can rapidly take over. It is a violent, forced collapse. The central mystery of Thackeray's globules is whether this process can run to completion before the entire cloud is evaporated into nothingness. Can a protostar ignite deep within that dark heart, gathering its mass at a frantic pace before its protective cocoon is completely torn away? The presence of these evaporating gaseous globules, or EGGS, suggests that some might just succeed. They are the densest knots within the globules, the last pockets to resist evaporation, and they could be the very sites where stars are fighting to be born. So while these dark specks appear small and fragile against the immense glowing nebula, they are actually cosmic battlegrounds where the creative force of gravity duels the destructive power of starlight for the future of a sun. The feathered serpent of Corona Australis weaves an intricate tapestry of shadow. Its form a writhing mass of dark filaments unlike any solid pillar or globule. This complex nebula looks less like a single object and more like a tangled nest of cosmic threads, each one a river of cold dust and gas. Such a delicate, filamentary structure immediately confronts us with a fundamental force shaping the cosmos, the invisible hand of interstellar magnetic fields. We cannot see magnetism directly, but the very shape of this serpent suggests its presence. The long, parallel, and curling filaments appear to trace the lines of an immense, unseen magnetic architecture woven through space. This field acts as a cosmic guide rail, channeling the flow of material along these specific paths and preventing the cloud from collapsing into a simple, formless blob. The profound question this raises is how this magnetic guidance directly influences the cloud's ultimate fate. As the gas flows along these filamentary highways, it gathers into denser knots. Is the magnetic field dictating exactly where these knots form, pinching the cloud at specific points to create the seeds of future stars? Or does it simply organize the material, with gravity taking over to do the final sculpting once a critical density is reached? To visualize this hidden force, astronomers employ a clever technique involving polarized light. As starlight travels through a cloud filled with magnetically aligned dust grains, its light waves become polarized, vibrating in a preferred direction. By meticulously mapping this subtle polarization across the feathered serpent, we can effectively draw a map of the magnetic field lines threading through the darkness. The resulting image is breathtaking, showing a ghostly skeletal structure of magnetic force superimposed over the dark filaments, revealing the invisible scaffold upon which this entire stellar nursery is being built. It demonstrates that the birth of stars is not a random collapse, but a directed and organized process, choreographed by forces we are only just beginning to see. A supernova's ghost is crashing into its own cradle. This is G350.1-0.3, a dark nebula caught in the violent aftermath of a stellar explosion. We are witnessing a rare cosmic event where death directly confronts its origins. The expanding shell of debris from the supernova remnant is now slamming into the cold, dark cloud of gas and dust from which the doomed star was likely born millions of years earlier. This collision of extremes, the hottest, fastest material in the universe meeting the coldest, most quiescent, creates a phenomenal laboratory. The initial shockwave from the blast does something extraordinary. It acts like a cosmic hammer, delivering an immense and sudden pressure that races through the dark cloud. This can crush stable pockets of gas, squeezing them to densities they could never achieve on their own. In this forced collapse, gravity finds its opening. What was once a stable, dormant nursery can be shocked into a frantic new wave of star formation, a second generation ignited by the death of the first. But the supernova's gift is twofold. As the shockwave compresses, it also pollutes. The cloud is being seeded with a rich inventory of heavy elements freshly forged in the supernova's heart. Atoms of iron, oxygen, silicon, and gold, created in the final moments of the star's life, are now being injected directly into the dark nebula. This enriched material will become part of the next generation of stars and any planets that form around them. It raises a profound question about our own existence. Was our solar system and the iron in our blood born from such a cataclysm? Did a long-dead star's explosive end provide the very elements and the trigger needed for our sun to ignite? G350.1-0.3 blurs the line between an end and a beginning, suggesting that every act of cosmic destruction might also be a silent contract for new creation. But the quiet of a cloud like LDN 1774 may be an illusion, a stillness enforced by an invisible hand. One of the greatest unresolved puzzles in all of astronomy is the precise role of magnetic fields within these dark nebulae. Are these faint cosmic force fields strong enough to physically support an entire cloud of gas, propping it up against the relentless crush of its own gravity? This single question is central to understanding why star formation seems so inefficient across the galaxy. The challenge is that these magnetic fields are extraordinarily difficult to detect. They leave no direct glow, no visible signature for our telescopes to capture. To measure their subtle strength, astronomers must rely on two ingenious and demanding techniques. The first involves a quantum phenomenon known as Zeeman splitting. As radio waves from certain molecules travel through a magnetized cloud, the magnetic field causes a tiny, telltale split in their frequency, a shift so minuscule it is like trying to measure the width of a single human hair from a mile away. This split, however, gives a direct measure of the field's strength. The second method uses the dust grains within the nebula themselves. These microscopic particles tend to align themselves with the magnetic field lines like tiny compass needles. When background starlight passes through this dust, its light waves become polarized, vibrating in a preferred direction. By meticulously mapping this polarization across the entire cloud, scientists can effectively trace the ghostly outline of the magnetic field's architecture, revealing its direction and structure. If these observations reveal a strong, ordered magnetic field woven through LDN 1774, it would mean the cloud is caged. The field acts as a rigid scaffold, providing crucial support that prevents the gas from collapsing. This could keep the cloud in a state of suspended animation for millions of years, dramatically delaying the birth of any stars. But if the field is weak or disordered, then the cloud's fate hinges on a far more delicate balance between its internal warmth and its turbulence. The answer defines the timeline of the entire galaxy. Do magnetic fields put the brakes on star formation, acting as a cosmic regulatory system that prevents all the gas from turning into stars at once? Or is their influence merely a gentle nudge in a process ultimately dominated by gravity and chaos? The silence of a dark nebula may not be a sign of emptiness, but the deep quiet of a standoff between two fundamental forces of the universe. From the silent sphere of Barnard 68 to the violent frontiers of the Cone Nebula, our journey through these 25 dark clouds reveals a universe teeming with hidden purpose. These are not empty voids or simple holes in the starry fabric of our galaxy. They are the cold, dark cradles where stars are born, the cosmic laboratories where complex molecules form, and the dynamic structures that shape the very architecture of the Milky Way. They challenge us with profound questions. What final trigger ignites a stellar nursery into a blaze of new suns? How do the invisible forces of magnetic fields and turbulence choreograph the collapse of gas into planets? And what does the strange silence of a cloud like the brick tell us about the extreme physics at our galaxy's heart? Each dark nebula is a piece of this grand puzzle, a shadowy question mark written across the night sky. So the next time you gaze up at the Milky Way's glowing river, look again at those dark rifts and lanes. See them not as emptiness, but as the universe's greatest reservoirs of potential. See them as the unlit wicks of future suns and the hidden workshops where the ingredients for worlds, and perhaps even life, are first assembled. We have explored 25 of these enigmatic shadows, but the mystery is far from over. Which of these dark nebula captures your imagination the most? Was it the fleeting beauty of the Horsehead, the profound silence of the brick, or the violent rebirth within a supernova's grasp? Let us know your thoughts in the comments below.